All right, so now we're moving back into doing this next part. So this is a new formula, and if you just look at this formula, you can see we're calculating a z. And whenever you see z in statistics, I want you to start to think about this image right here, which we learned back in the day. And your z-score is the number of standard deviations some point is from the mean, right? And so here we're going to create some new z-score. And you can see that we have some point here. It's our sample mean. And how far is it from the hypothesized population mean? And you have to remember what this notation means. If you don't know this notation, right, statistics is really hard. And that's why I put together this little sheet so that for us, statistics is easy. And you can see here when and I'll just bring this actually over to the side so we could see it while we also look at this one with the formula. But we could see x bar is the sample mean, right? Sample mean right there. And we could see that mu is the population mean. And this is mu with a subscript of 0. So that's the hypothesized null value, right? The hypothesized null hypothesis for the population mean, the population mean for the null hypothesis, right? And so we're saying this point, the sample mean, how far is it from this hypothesized population mean? And then we're dividing that here by the standard error, which is also the standard deviations. And so z, just kind of building on what we've learned, I'm going to bring this one over too, right? Z is the number of standard deviations a point is from the mean. So here we're finding a point, right? It's the sample mean minus the hypothesized population mean. That's some amount. How far is the sample mean from this hypothesized population mean? And then we're dividing that by the standard error. And the standard error is the standard deviation for the sampling distribution. Okay? And so over here, when we learned about this first, we did it by the standard deviation here. And that was standard deviation just for sample. Right? So that S right there. But here we're doing the same thing with the Z. It's like there's some point, how far is it from the mean? And then we divide that by standard deviations, a single standard deviation, to find out the total number of standard deviations or the fraction of a standard deviation that this point is away. That's what Z is. Okay, and that's your standard error, which is your standard deviation for a sampling distribution. So when we do this calculation here, and let me just bring up that. We already saw this slide. So the next slide here is just showing you this picture larger. But here's where we do this next calculation. So let me bring, I guess we'll just look at this one bigger until we need both slides. And so when you see this, we plug in these numbers. We get our Z is going to be 2.92. That's our sample mean minus 3. And 3 is the null value for the population mean, right? So it's the hypothesized null hypothesis for the population mean. So we get the sample mean minus the hypothesized value for the population mean. And then we divide that by this information right here, which is our standard error. And then when we do all that, we get Z is equal to this, and then Z is equal to negative 2.67. Well, negative 2.67, if we go and we look at our Z chart here, negative 2.6, and bring it out to 7 is 0.0038, 2.67. So we got a Z-score of 2.67, which gives us 0.0038. And I'll add a negative in front of that since it's to the left side of the distribution curve, right? So you could add a negative in front of that. And then if I look at this picture a little bit bigger, so we have the Z of 2.67, you can see it right there, and you have the 0.0038 right here, right? And so this is actually an old picture. Let me get that old one and put this new one in here, Control C and Control V, and then let me just make this smaller, and there we go, we'll put it in there like this. Oh, come on, get bigger, get bigger, bigger, bigger. There we go. So we have 0.0038 and we have 2.67. So, and this Z here, this 2.67 is known as our test statistic, right? And we calculated it with this new formula, which we are given in Chapter 9, but it's really kind of just a new way of stating this idea that we're already familiar with. And so we get our z-score, 2.67. And based on that, we could go to the z-table and find out the probability. And that means the probability is 0.0038. And it's 0.0038 down here, right? Because it was way down here in the negative area, which means you're on the left side of the bell curve. So 2.67 is 0.0038 right there, right? 0.0038. And with those two things, we can now start to look up, what is the z-score and the probability for these other numbers. So if this is our 99%, and this is why it's a one-tailed test, because we're just testing to see if it's gone too low. If it's gone too low down here to the left. And it needs to be above this to pass, right? It needs to be above 0.01. It has to be in the 99% area for it to pass. Because if it's at 3 or more, right, more going out this way, you're okay. But if you're below here, if you're in the 1%, we're looking for a 1% level of significance and 99% confidence level. Right? We want it to be here for the population mean to accept and do not reject the null hypothesis. And then if it's down here, it's gone too low. And so we're doing this a one-tailed test because we're really looking to see if it's equal to or greater than some value. And so, we don't have a fail range out here because it could be as great as it wants to be and it's always going to pass. So our only fail range is down here if this got too small. Hopefully that made sense. That's why we're doing a one-tailed hypothesis test. And when you're doing a one-tailed hypothesis test, you're only looking to see if the fail range is down for something that's equal to or greater than. You're only looking, so this is like a left-tailed, one-tailed hypothesis test. You're only looking to see if something goes too small and it falls down here. So really our alpha, our level of significance, is the 1% right here. We're not splitting it between two tails. So it's just 1% right here. And that's our confidence level, right, is the confidence coefficient, the 99% is all out here. So with 0.01 right here, that means that like 0.01, this is like 99% of our data. And 0.01 gives us a 2.33 z-score. So if we go and we look at 2.33, so 2.33, right here is 0.0099, right? And so that's about as close as you could get to 1%. And remember what a z-table shows you is from this point over, is that's the probability. From here over is the probability. And so here we have at 2.33, we have 1%. Like that's like tenths, hundredths, thousandths. I don't know. What is that? 10 thousandths or 100 thousandths? I don't know. And I'm not motivated to ask ChatGPT right now. But that's the 1% right there, right? Close enough for government work. So 2.33 is our z-score. So when we know our 1% here, right, we could find what is the z-score associated with 1% being from here over to the left. And the z-score associated with that is 2.33. And since we know that our sample produced these numbers right here, and these numbers are less than these numbers, our sample fails. If our sample had landed out here in the 99% area, we would say, you know what, the population mean, we're gonna accept the null hypothesis. Like they say, do not reject the null hypothesis, and that means that this is the state, right? The current state, there's no change. But actually, because we don't fall on this side of it, we fall on this side of it, we say reject the null hypothesis. There's been change. It's no longer the stated value on the can, where the population mean is 3 pounds per can or more would be fine. But it's less than 3 pounds, and we have 99% confidence that it is less than 3 pounds. The population mean is less than 3 pounds. And so those two approaches to calculating these, this is called the test statistic approach right here, getting these values, the z values. And this is called the p approach, or the probability approach, getting those values. And so those are the two approaches that you use in Chapter 9 to analyze problems and to determine whether or not you reject a null hypothesis or you do not reject a null hypothesis. I like saying accept, but I'm going to try to say do not reject, but that just sounds too convoluted for me. So anyhow, that's the next part in this thing. And in the next video, we're going to take a look at the convoluted way that the textbook explains all this. So you could always come back to this video, the one you're watching right here, right now, and you could watch this again to remind yourself, what is a test statistic? What is the test statistic approach? What is the P approach, the probability approach? And it's just finding these two things and then comparing them. And always draw these types of little graphs out for yourself so you get a visual, and then just like put this probability here and the test statistic here, and just get your z value and then get the probability associated with it, and then just look at it. And for me, visually, it always makes sense. But and then the textbook wants you to memorize all these rules, like if this is greater than, less than, then you accept, or you do not accept if it's greater than but less than. And it's like, I don't want to memorize the rules. I just want to draw it out and like logically be like, yep, that's in the area where we reject it. See, it's in this area, we reject it. So we reject the null hypothesis, right? Because the population mean is not going to be equal to 3. It's something less than that. So that's the way I do it. It makes sense to me. In the next video, we'll take a look at the convoluted way the book explains it. See you in the next video.